The increasing need to introduce new products, the ability to utilize changing sources of raw materials, the uncertain supply chains are bringing complexity to process manufacturing every day. At the same time, you need to do this efficiently by using both your process equipment as well as your expert assets to your advantage. This means more variability to deal with. Two production lines designed to be identical don't result in the same yield and quality. There is variability from shift to shift. There is variability from batch to batch. There are ways to overcome this challenge, and process manufacturers have typically looked to process optimization software as a solution. But legacy and existing process optimization software is not a practical solution for most because of the cost and complexity. Typically, you have to build dynamic process models that require a lot of expertise and time. Even if you are able to implement these solutions, the lifecycle cost and maintenance generally don't allow us to sustain these systems. These solutions are therefore not financially viable for most process manufacturers. AI and machine learning provide an alternative, and one must look to these alternatives. But most of these solutions are based on big data algorithms and techniques like reinforcement learning, which we have built and implemented, but the large data requirements and the high compute cost make ROI difficult to achieve in most cases. It is like replacing a complex legacy solution with a complex modern solution. There has to be a better way. There is a small data-based machine learning algorithm for process optimization that we have developed and successfully deployed. We don't need large historical data sets to train the models. We don't need to build complex first principle dynamic process models. Instead, we focus on simplicity, speed of deployment, and a fast path to ROI. So rather than building prediction models with big data algorithms, we leapfrog straight to process optimization with a small data algorithm that improves the process while it iteratively learns.
So with that overview, I'll open up the Quartic Process Optimizer application so we can see it in action. First, I will start off by giving my project a name, and next I will set the project conditions. And in this case, I will be optimizing the yield on a penicillin fermentation process. First, I will choose the objective I want to optimize. I want to maximize my yield. And I don't have any historic batch runs in this case, so instead I'm going to use my recipe as a starting point. Within my recipe, here are the different process parameters I want to control. I have a starting value for each of them, and an upper and lower search space for each time interval of my batch run. This controls how much the optimizer can adjust each one of these parameters, and this is shown visually over on the right-hand side. The dark orange line is my starting point for the optimizer, and the lighter orange band is the allowable search space, and I can see this for each one of my process parameters that I'm going to control. So that's it. Those are the only inputs that this optimizer needs to run. I don't need a huge historical data set, and I don't need a mechanistic model. Now that this is all set up, I can set a number of optimization runs because I'm not running this in real time on an actual process. What's happening here is the optimizer will make set point recommendations, feed that into a penicillin simulator I have running in the background, and that simulator will provide the real-time sensor values and quality values that then get fed back into the optimizer so it can iteratively learn on those results, and then provide a new set of recommendations for my next batch. So using the simulator, we'll see this iterate quickly over 10 batch runs, rather than need to wait days or weeks to see batch runs complete. We can see each batch run running in real time, and our overall yield as the optimizer works. Over on the left-hand side here, these are the actual set point recommendations coming out of the optimizer for each time interval of the batch, and I can see this for each of my process parameters as I click through these. Then down at the bottom, these are the trends of the actual sensor values coming out, so the variables that we're controlling, but also some of the other variables that we're not directly controlling, things like my pH or my concentration. So as this iterates, we're able to see how each one of our batch runs comes in. We can always see our best yield run so far in this lighter gray versus our current run. And as the optimizer narrows in on the optimal settings, the yield begins trending upwards and will then level off and produce consistently higher yields than before. And that's the goal: better, more consistent results. And because our optimizer is designed to run and learn in real time, it can take into account the ever-changing conditions of your process or of input materials and incorporate that variation into new setpoint recommendations. And in this demo so far, I've shown an online version, meaning we're live streaming data from equipment and sensors, but we also have a web-based offline version where you can simply upload an Excel file or a CSV file with your data, select your parameters, train the optimization model, and then view your predictions and setpoint recommendations. In a matter of minutes, you can optimize your process. Simple, fast, and effective. Start optimizing your process today with Quartic's Process Optimizer.